Hello, everyone. We are having a little bit of audio issues here, so I'm just going to go ahead and get us started. My name is Max Rohr, and I'm going to be going through the webinar today. We are going to be talking about heat pump water heater fundamentals. So I'll give you a little bit more of the background as we get started here and go through a couple of housekeeping slides. So if you have issues with GoToWebinar, best case scenario, like we're having today, log out, log back in, and that usually fixes the audio and it'll be a little bit faster. If you want a copy of the presentation, we're happy to provide a PDF, as well as we'll archive this on YouTube. This is what the certificate of attendance looks like. So if you can self-report this in your jurisdiction, we'll send you one of these. Just hit yes at the end in the webinar survey. So this is kind of an exciting issue of hydronics that is going to dovetail with Coffee with Caleffi today. So available today on hydronics.caleffi.com, we have heat pump water heaters fundamentals. This is the 33rd edition of our hydronics journal. So this will be a PDF and a hard copy. If you have signed up for a hard copy, you'll get that in the mail. And you can also do that at hydronics.caleffi.com. If you'd like to receive one of those, we'll also have the PDF that you can download in the next week or so. But today it is live on hydronics.caleffi.com. So that's kind of our long scroll magazine kind of digital edition that has additional resources and links and things like that. So next month, we are going to have John Siegenthaler back at the head of the class. So this will be an interesting one because he's going to talk about a specific case study that he did. So this is an air to water heat pump project that he did and is going to, it's been, I think, 18 months or so since the original installation. So he'll talk about some of the wins and losses and things that he would do the same and differently in the future. So join us next month on the 24th for that one. And today, this is me. My name is Max Rohr. I'm the Education and Industry Engagement Manager here at Caleffi North America, and I'm going to walk you through the next set of slides. So what are we up to today? This is the agenda on the screen here. I'm also just going to kind of talk about this topic a little bit because it has been wildly popular, I would say, is one of our Coffee with Caleffi topics. We had a lot of signups for this webinar. So kind of some background, as is the case with any mechanical equipment, proper application and installation leads to optimal results. So heat pump water heaters are no different from other equipment. They're selected installed in ways that maximize their COP and have the potential to reshape the way that we do water heating for the entire North American market, while increasing the ability to use renewable energy, which is a big piece here. It isn't just a switch from electrification from gas to electric just for the sake of doing it. There is some benefit overall to both of the Canadian and the American attendees today by going electric, but it isn't the end all be all thing. So we could help building owners lower their utility bills while adding some benefits to the grid by decarbonizing and shifting the load a little bit, which I'll talk about in more detail. Today, I'm going to identify the fundamentals for site evaluation to determine if a heat pump water heater is going to be a good fit. More of this will be in Hydronics 33. If you want a 54-page version of what I'm going to say today, that's going to give you a little bit more of the math and background and specifics. So we don't sell heat pump water heaters at Caleffi North America. I'm not going to say that heat pump water heaters will be the everything for everybody, everywhere technology for heating water, but it's something that as industry professionals, we need to pay attention to. It's as if you called 911 and said, hey, I need an ambulance. And they say, oh, the ambulance we have outside is a Ford and I only drive Chevy. So you're gonna have to call somebody else. So we are the professionals. We are the ones that know how to apply these different technologies. A heat pump water heater is just another tool in a plumber's toolbox to figure out how to best supply hot water to a building. So we'll go through some of the things that are pre-submitted questions and some prerequisites to figure out if and when and how a heat pump water heater not only could work, but would be set up for success. That's what we want to do with any equipment here. And as component manufacturers, we want to make sure everything upstream and downstream of our equipment is going to work well. So that's a little bit of the background. We received a lot of specific pre-submitted questions that we'll get back to you. Either a couple of them are going to be mentioned as we go through here, and otherwise we will follow up after the webinar and either get an answer to you or point you in the right direction if it's something that we have not really core competency in, like refrigerants. There were a couple of refrigerant questions. who knows what the refrigerant of choice is going to be in another 6 months or 6 years or whatever. Okay, that's the background. To start with, I'd like to get a gauge of the audience. So are you designing or installing heat pump water heaters today? Is this something that is an always, we do this every time, often, rarely, or never scenario? So we'll see if we can get that poll to launch. We had a little bit of issue with the video here, but it looks like it's coming up. And one of the background things that I think is kind of relevant and interesting related to heat pump water heaters is that the term plumber refers to the material of lead in Latin. So that's where the plum came from. That's the name for it. We have been a part of a lot of different technology shifts as plumbing industry professionals over the years. So heat pump water heaters are no different. We used to be a lead trade where we would make things out of lead and move stuff around with lead. That obviously is not something we want to continue to do. That technology has changed in the same way that heat pump water heaters are a new thing that we need to evaluate, and something that may be a much bigger part of the market in the future. Currently, heat pump water heaters are somewhere around 2% of market share, but it's something that could expand really rapidly. Okay, so the results are in. We got 5% always, 15% often, 44 sometimes, and 36 never. So that's kind of I guess what we expected to see there, that this is something that the always is still a pretty rare scenario, even in the early adopter states like California. Okay, so according to the Advanced Water Heater Initiative, which is a really interesting group, an industry group to keep an eye on, they are doing a lot of this research and a lot of the background and a lot of the feasibility study things. But what I'd like to point out is that more than 25 million of these systems, of the domestic hot water systems in multifamily and single family buildings, over the next 10 years will need to be replaced. There is kind of a pretty quick natural turnover here compared to things like power plants or bigger infrastructure things that don't turn over except for every 40, 50 years. This is something that happens all the time. How do we prepare for that in order to move forward as an industry, and what's the best foot forward? Okay, so what are we trying to do just as industry professionals in general? We're trying to heat water in a cost-effective manner for our customers. We also want to make sure that we're delivering that water. The hot water is hot, the cold water is cold. We're not scalding people. That's what we're trying to do. That's kind of the big picture. So what is the shift? What's changing now? So big picture, kind of across the US and Canada, we are incorporating a lot more renewable energy. It's coming on to the grid very quickly. This is something that the technology is moving rapidly in North America, and in the States specifically. We have a Western interconnect that actually will transfer some power from Canadian Hydro near Vancouver. Same thing in Ontario for the Eastern interconnect, that's kind of a share of electrons across the border there. Texas is an islanded grid. Islanded, I guess, is the appropriate utility terminology to use. Texas is its own grid, which is kind of interesting because they can decide what their mix of power plants will be without really having to check with anybody. The downside is they can't pull electrons from other places if it gets really hot or really cold, and the path to electrification could be trickier because they don't have as much backup that they could pull solar from Arizona or something like that, the same way that California could. So why is this happening so fast? Mainly because the cost of solar has come down so rapidly. So if we look at the residential PV cost has come way down, the utility cost has come down even further. So this is the reason we're starting to see a lot more solar come into the mix of energies that we have in the grid. Here's another forecast by the US EIA. If you look at this graph in the next year, 23, 24, we're going to see a lot of 68% of the new infrastructure at the grid level is going to be solar, either on homes or utility grade, kind of big PV installations for out in a field somewhere that goes right into the utility. If we look at the other things that are coming online, we don't have as many of these other technologies coming through. So nuclear is kind of an interesting example. For the first time in 30 years, we have 2 new power plants that are going to come online in 23 and 24, both in Georgia. New, I guess, meaning they were permitted after 1975, not delayed construction. But nuclear isn't here to save us in the capacity that we need. Maybe that will change. If the permitting process for nuclear speeds up, that could be a different story. Currently, they're projecting that we're going to have less nuclear capacity by 2050 than we currently have. So nuclear isn't set to balloon the same way that solar is. There's a problem with that, though. It's a good problem to have, I guess. We're getting all this new renewable energy into the grid, but if we look at this California duck curve, so that's kind of the shape of the curve here, we're bringing on more solar during the day when the sun is up every year, but our net load actually went below zero here at one point this year, which means we had more solar panels pumping power into the grid in California than we could use, because we don't need all that power at 1:30 in the afternoon. The underlying problem is that we need to reduce the energy efficiency of things, but we also need to find a better way to spread out the solar energy that we're harvesting during the day. It could be the same thing with wind, that we need to find a way to make it seem like a really consistent flat curve of power that we're getting, so the net doesn't get so wild like this, because there's a potential that we could make this duck curve better or worse with what we're going to talk about today. So can we do this? Can we reduce the amount of energy that we use at the tail of the duck in the morning and at the head of the duck at the end of the day, but also use all this solar energy to charge something during the day? Instead of saying we've got too many solar panels, we're going to have to unplug some because we don't have anywhere to put all these electrons, we need to charge the batteries during the day. So how do we do that? So one of the things, as kind of a side note here, is that a background for heat pump water heaters is that the Department of Energy has just a couple days ago, on July 21st, said that we are looking to a future where we're almost going to mandate heat pump water heater technology and condensing technology for gas appliances as just the way forward. So everything we talk about today could change depending on how these energy efficiency rules with Energy Star or the Department of Energy move forward. This is still a ways out, but it would be a faster move to a different technology if something like this did go through and hold. So back to the battery piece, one option we have is to charge a lithium ion battery or similar, something like that, where we take all the electrons during the sunny parts of the day and we charge up a big battery. I've got good news for you. Overnight, we went into all the homes in North America and installed a big battery. It just looks more like this. This is our battery. We may still have these big Tesla batteries in everybody's garages, but that's all new technology that needs to be added to a lot of different mechanical spaces, a lot of different homes across North America that does not currently exist. Most of us have water heaters. Most buildings have a storage vessel water heater, except for the ones that have tankless water heaters or something like that. But we have a big battery in a lot of homes. This is what I would argue we need to charge up with that excess solar that we're going to have in the middle of the day. So our goal here is to lower the operating cost of water heating without interrupting the delivery of hot water. We could just say, hey, we're only going to use solar for hot water in the future, so make sure you take a shower while the sun's out, because when the sun goes down, you're not going to have any hot water. That wouldn't be that popular. That wouldn't be helpful for our customers. That's not going to be a good fit. So we need to figure out a way to deliver hot water to our consumers when they need it. The problem is most consumers want to use a lot of electricity when they wake up and get ready for work, and then when they come home from work and get ready for dinner, things like that. This is what we need to avoid to make that duck curve not as bad. So domestic hot water is about 20% of the residential end use energy consumption in the US. This is a big needle that we can move with domestic hot water if we can do it a little bit differently. And I'll show you kind of at a utility level what we would do here. So today, if we just replaced everybody's gas water heater in North America with a heat pump water heater, there is a potential that we could actually make this duck curve worse, because now everything that was a gas appliance has been shifted to electricity, we now have more electricity needed to heat that water in the morning when we're getting ready to go to work. We have a lot more solar, so that's good, but we also are bringing a lot more electricity into the grid in the evening. So just switching to heat pump water heaters without changing our schedule a little bit could be a recipe for more of this duck curve, and it doesn't solve as many problems as we would hope. There are still plenty of benefits, but this specific thing could get worse. Here's what we could do differently, and this is absolutely possible. All these technologies that we're going to talk about today aren't some pie in the sky things. These are machines and technologies and communication protocols that we have today that we could use. So the idea would be to charge our thermal storage battery, our tank water heater, before these peaks. So if we have the heat pump water heater turn on early, turn it at 4 in the mornings before 6 a.m., and then try and let it coast through that peak, and then do the same thing during the day. We've got a lot of solar energy. Let's charge up this water heater before we get to our peak utility rates. There are a couple different things that we benefit from here. One, it's going to be less expensive for those same BTUs if we just shift off of that peak utility rate window. The other thing is that we can do this in a way that the homeowners don't even know that it's happening. The return on investment will be quicker if we're heating water off peak all the time. The analogy that I have here is it's as if you could grill a hot dog at your house before you go to the baseball game, or you could buy one for $26 at 3 p.m. when you go to the baseball game. It's kind of the same water heating analogy. We don't need to pay more to heat water. We can shift off peak. So what we could do, if this is just the curve kind of added by water heaters, is we could unduck this duck curve in a sense. We could heat the water early, coast here, and start to level off this duck curve just with water heating, because as I mentioned before, it's a pretty significant amount of electricity that we could use and could shift differently from what we're doing in the past. So now here's where kind of the Caleffi products come in a little bit, and not Caleffi specifically, but just components for a plumbing system. So this is where mixing valves are going to be very helpful for this procedure. If we just start charging the water heater at 4 in the morning and through 6 in the morning, the temperature could be really hot, could be unacceptably hot to send to a shower. That 6 a.m. shower, we do not want 142 degree water to come out of that shower. That's unacceptable. So what we can do with the domestic hot water components that we have here with mixing valves is temper that. So we're not sending scalding hot water out to the system, even though in the background, the temperature inside of the tank could be all over the place between 125 and above 140, depending on the day. So here is one of the key things that I think is going to be missed in these early adoption move to heat pump water heaters and don't ask any questions really quickly scenarios. If you had a gas water heater set to 115 degrees today and you just did a cut and paste and put in a heat pump water heater and a mixing valve, so you could do some load shifting without the high temperatures leaving the mechanical room, here's what could be missed. Most thermostatic mixing valves will have a temperature differential between the hot inlet, so the hottest point of the tank, and the mixed outlet of about 18 degrees. So if we just put in a heat pump water heater and set it for 115, we are going to have sub 100 degree showers. And that's something that could throw a homeowner for a loop and say, what is happening? We used to have nice warm water all the time, and now we're taking cold showers. This heat pump water heater was a mistake. So that's not a deal breaker. It's just something that we have to pay attention to, because we're going to need to store warmer if the expectation is to have 115 degree outlet temperature water. We need to overcome that 18 degree temperature differential with most thermostatic point of distribution mixing valves. So that was a pre-submitted question as well. This is a new thing that may not have been in the building in the past. Good news. If we're looking at commercial projects, one of the major kind of component technologies that will help us out a ton in this realm is that, oops, back slide, point of distribution mixing valves like this ball valve control element style, so this is an electronic mixing valve, not a thermostatic, may not have any temperature differential between the hot and the mixed outlet. So this valve can do 100% hot. So if you stored your tank at 115, you could just send 115 right out to the building. There's no 18-degree penalty there. So for commercial projects, this is really important because this can come into play with return on investment and COP, that we don't need to heat the water to 150 degrees in a commercial building to get 115 out. We could just mix right at that same temperature and let that go right out to the building. So no need to store warmer, but it could still be beneficial as far as capacity goes. The other component that could be helpful here, depending on the application, is a point of use mixing valve. So instead of having a point of distribution mixing valve in the mechanical room, if we have other high temperature components in the system that need warmer water, like 140 degrees for a dishwasher in this example, we could also put point of use mixing valves in these different spots and not take the penalty in the mechanical room, just have that temperature differential right by the fixture. That's another way that we could go. So what are some of the other pros and cons of storing warmer? So upsides, that if I took a 60-gallon water heater in Atlanta, Georgia, and I stored it at 140 degrees instead of a baseline of 120 degrees, I add 34% capacity to that. So I could make a 60-gallon water heater effectively feel like an 80-gallon water heater just by storing it warmer and mixing back down. So we've added capacity without adding mechanical room space, without adding cost to the heat pump water heater to go to a bigger size or anything like that. And this isn't just for heat pumps, this could be for gas or electric or anything else. Just by storing warmer, we can add that tank effective capacity because we're mixing a smaller portion of really hot water with cool water. And that can be a good way to go. That's something that's been in our toolbox this whole time. We gain the mixed temperature consistency as well with a point of distribution mixing valve. So what are the downsides to this? And this will apply with everything as well. So if we stored, as an extreme example here, which I wouldn't recommend, but if we stored in Atlanta at 180 degrees, we would gain 103% capacity in the mechanical room. That would be great. I'm going to tell you that you would scale a mixing valve a little bit faster. If you had 180 degrees in your mechanical room all the time, that's going to have scale kind of cook out of solution and cook to brass and copper and all the components in the system a little bit faster. So that's going to affect some of the serviceability of different things. You're going to have to maybe clean those point of distribution mixing valves more frequently, or even replace them if it's an extreme case. The other thing is that if we stored it at 180 degrees in my mechanical room downstairs, that whole basement's going to be pretty hot. We're going to lose some of those BTUs just in the delta T to the mechanical space, and that can be a disadvantage as well. We're going to have really warm mechanical spaces, and we're going to have to refire that water heater to maintain 180 degrees more quickly if that delta is really big. So one of the pre-submitted questions that we have had and we have looked into a lot as we put together Hydronics 33 is, what is the full story with the COP? So like AFUE ratings, right on the side of a boiler, you're going to see an AFUE stamp of 95 or 96 or some big number like that. But that's not a guarantee of performance. And I would argue that that's very rarely the case with boilers as well, unless maybe you were doing a snow melt system or something like that, where you've got really low sustained return temperatures that you would see those big AFUE numbers if you had a combustion analyzer. Like the boilers, the COP for heat pump water heaters is going to depend on a few different factors. It's going to depend on how hot we're trying to get the water. Some of that's based on the different refrigerants that you use in the system. Some of them like to operate at higher temperatures. Some of them don't. Some of them would get to a point where your COP is going to be really low if you're trying to get 160-degree water out of a heat pump water heater. The other thing is, how warm is the surrounding air? So if we're trying to do a COP calculation in Alberta, we're not going to be as happy with the performance as we would have been in Florida, just because the air in Florida is so much warmer. It's so much easier to get that out of the ambient and pump it into the heat pump. Just a little bit less energy required to do that. But we can calculate some of these things. And as an aside, I've talked about gas water heaters quite a bit so far, gas gas water heater technology. If you're on electric, your COP will be only ever one, if it's just electric resistance. So heat pumps as a technology shift from just electric resistance in places where hydro is cheaper are going to be a really big upgrade in a lot of cases. So you can go from a COP of maximum 1 to somewhere in the 3 to 5 range potentially with a heat pump water heater, and that could really make a big difference. So the COP we're talking about here, how much energy does it take to run the compressor? How much does the power required to do that, and the heat absorbed from the source, from the warm air surrounding the unit, and then how much can we move out to the load here. So let me go through just an example of the math. So if we're looking at a simple COP, we have a heat pump water heater that is going to a 2400 watt heat pump water heater that's going to deliver this number of 30,000 BTUs per hour. We're looking at a 3.66 in this ideal scenario. So that's still 3.6 times greater than what we would have done with just that electric resistance element alone. So that is a major upgrade. What are we going to expect in different parts of the US? I don't have a graph like this for Canada, but you would probably, you can look up the ASHRAE data for the climate zones. The IECC climate zones is kind of what these are based on. And this is a pre-submitted question as well. So what if I wanted to put a heat pump water heater in an unconditioned basement? Depends on where you live if you're going to expect to get a lot of high COP range out of that equipment, or if you should probably expect that you're going to need electric resistance to carry a decent amount of the load, and your COP may be closer to that bottom of the range. So this map is helpful to kind of get a baseline here. This is part of the reason that heat pump water heaters along the Pacific coast have moved really fast. Part of it is policy, part of it is climate, that this is just a pretty good landing spot for a heat pump water heater to be able to move the temperature from the ambient into the room in a variety of locations. If you are in Salt Lake City, like I am today, we're probably not going to want a garage or an uninsulated room. One of the things that I was talking with Brian Dooley at Osborne Company, one of our reps out in California, they're saying, yeah, you could put a heat pump water heater in your garage in Salt Lake and you're going to have a very cold garage in the middle of winter. So it's taking the little bit of warmth inside of that garage and putting it into the tank. So you could walk out from the kitchen into your garage and have it be colder than outside, which is something to at least anticipate in these systems. So in a lot of cases, an interior room, a basement is going to be the best place to go. Now, here's the more complicated story with COP. Let's say I have a new heat pump, air to water heat pump for space heat outside, and I'm going to heat my building, my house with this heat pump. We're going to heat all the air inside with the heat pump. That has a COP potential of 4. And then I put a heat pump water heater in the mechanical room that has a COP potential of 3. What are we actually talking about here? And this was another pre-submitted question, is how is the COP affected if we have 2 different things here? So if we have the COP here, is this on an island if it's pumping heat into the building? And the answer is no, and it would be the same answer for a 82% gas furnace. We're heating the space that then this heat pump water heater is absorbing this heat from our furnace or from our heat pump into the tank of water and cooling the ambient again. So now our heat pump or our furnace has to work a little bit harder to recover that. I don't have a formula that's going to do all that math at the same time. It would depend on how warm you keep your house, all of those space heating considerations, as well as how much hot water do you use. Is this something that I have in this house, a couple bathrooms, it's just my wife, my daughter, and I. We don't use a ton of hot water compared to if you had 8 bedrooms of people using the shower every day. Then you're really going to make that furnace or that heat pump work hard to keep up with the space heat. And the end result in this example that I mentioned here is your total cumulative COP is only 2. If you're cascading these heat pumps, it's not a 4+3 scenario. you're going to have to make that the total assumption is that your COP is going to go down. Again, better than one, better than electric resistance for everything. Big upgrade there. And the hard part is, how do you evaluate that versus the absolute best case scenario of a condensing boiler with an indirect tank? I don't have a formula that's going to spit out that perfect crossover example there, but this is how you'd at least get a little bit further down the trail to figure out what to expect. Okay, let's go over some installation considerations here. So let's say we're talking about a new project, and the example that we use in hydronics is in the perfect world, the architect, the engineer, the plumber, the homeowner, all the stakeholders sit in the room and they say, we want to design this entire building around a heat pump water heater. How would we do that? I know that that's a very far-fetched thing. That's not going to happen in most cases, but what would that look like? What would best case scenario for every single component look like? So where are we going to put the water heater? Is it in a garage if we're in Salt Lake City? Maybe not. Maybe it's in the middle of the building. Maybe it's in a warm spot where it has a lot of cubic feet to kind of absorb energy from. Something that ideally is a room with more than 700 cubic feet would be a good place to start. The air temperature, we're expecting it not to get below 45. If it's 70 degrees, that's great. Know that you are pulling that heat from something else, from your furnace or from whatever the space heat component is. So do we have good access to all these different things? In a new construction scenario, we could have communication wires and our electrical service entrance and the place where we're going to distribute the hot water out to the building all in the same spot. Maybe that was part of the plans all along, maybe it wasn't. We'd like to gather all those things to the same spot. One of the technologies that I won't talk about a lot today is the trade name before was EcoPort, and it was kind of a water heater consensus that they're working on in coordination with the Advanced Water Heater Initiative. It's a communication protocol between the utility company and your heat pump water heater, where in events that we're closing in on a brownout, they could lower the set point of your water heater and limit the cycles there. That type of communication into these mechanical spaces could be helpful. In the past, maybe we didn't have any sort of Wi-Fi or Ethernet access in a new mechanical room. That could be something that could be beneficial in the future and could reduce your utility bills, because sometimes those are rebate programs. All of that is kind of up to your local zip code to figure out if they have programs available for things like that to stay off peak, and as well be a part of that EcoPort protocol to communicate with the utility company. Could be a good fit in a lot of cases. Maybe is something that's not the best fit for your home, but is worth taking a look at. And kind of the spirit of this hydronics issue in this Coffee with Caleffi is to at least know that if you're building something new, should I plan for this eventuality? Should I have this in one spot that in the future, even if we do a gas powered water heater today, is that going to be what we have for the life of the building? The answer is no. Maybe it is gas in the future, but it's probably going to be something different. There are going to be new energy efficiency standards and codes, and communication may be a bigger part of mechanical rooms, as well as with heat pump water heaters, the ability to use more electricity. So we may need a slightly bigger electrical service if it's a new building. That's probably not an enormous cost difference compared to retrofits, where I'll talk about that a little bit more with some options as far as another way to go forward without upgrading your panel. So those are a couple of things to consider. Condensate is a new output here. So my gas water heater in the basement doesn't need to be piped to a floor drain. It's not generating condensate. It luckily is above a floor drain in case it leaked in our house, but that is going to be a new output. So if you just put a heat pump water heater in the garage, you now have a drip of condensate that you need to put somewhere, into a drain, or pump it to another part of the building or to a drain, making sure it's not going through an unconditioned space where it could freeze, or you're going to have that condensate build up somewhere else. So those are a couple of the pieces. Heat pump water heaters are going to be a little bit taller than just an electric, if that's what you're using now, because you have to make room for all that heat pump on the top. So that can be a consideration. Garages are a good spot if your climate will allow it for a retrofit or for a new heat pump water heater, because if you add more storage, we're talking about a lot of weight. We can't just put 500 gallons of water on the top of an existing commercial building in some cases. That's gonna be a lot of weight to add to the plan later. If we're looking at this at the beginning, we can say, hey, we want to, for this commercial building, have 500 gallons of storage, potentially for a big hotel or something like that. Where do we realistically want to put that in case it leaks, in case we have issues in the future? Do we want that in the parking garage, or do we want that way up in on the top of the building that we would need a crane to get it up and down? Those are things to start looking at now that maybe weren't as big a part of the scope in the past. So what's our storage temperature? Would a point of distribution mixing valve be helpful? We could do 500 gallons of storage with no mixing valve. In some cases, I don't know where that would be a good fit. I don't know if there's any code that it would actually be the right size building to do that. Or do we want to do 300 gallons and store it a little bit warmer? Those are some big questions to ask right at the beginning, because that could make an enormous difference in the installed cost to just do an electronic mixing valve and reduce the size of the tank quite a bit. Another big one that is very closely related to this is the domestic hot water recirc. So in the past, I would argue, gas appliances covered up a lot of really poor performing DHW recirc systems. So I think there are a lot of buildings in the US and Canada that have recirc systems that go down into a crawl space with uninsulated copper and go 100 feet that way and come back, not balanced right. And you're just dissipating a lot of energy into the unoccupied spaces, which is actually increasing your cooling load a little bit in the summer. Not ideal, but the gas appliances maybe just covered that up. Maybe they could just keep up with that and then also keep up with the load on top of that. With heat pump water heaters, we need to pay attention to DHW recirc, because we don't have the ability to just overcome a lot of wasteful DHW recirc with the heat pump. It's not going to recover as quickly as a gas appliance. That's okay as long as we're not wasting a lot of energy with the recirc line. Heat pumps won't fix recirc lines if they're wasteful, which I'll talk about more with the retrofit projects. So in a retrofit, I've talked about this a little bit, the water heater weight is going to be really important. Airflow, I would say, is the new one that we have to pay a lot of attention to, that in the past, maybe it wasn't as big a deal for an atmospheric water heater. We had to have kind of a certain amount of space or inputs to do that. In order to get to those high COPs with your heat pump water heater, we need to have a good flow of air to get warm air. Ideally, if we have 700 feet of warm space in a mechanical room that's under a house or something like that, that's great. Check with your equipment manufacturers to get the specific numbers there. Unfortunately, in retrofits, we're going to be looking at a lot of different places where the water heater was hidden in a closet or in a small mechanical space, or somewhere that there is not 700 feet of space for it to pull heat from. There's not going to be that much room. There may be some really small closets that we need a fully louvered door. Might need to do top and bottom louvers. All this is going to be set by the manufacturers. In some cases, maybe really beneficial, instead of pulling the heat out of the basement, to pull it from outside. So in Salt Lake City, it's 100 degrees again today. I could pull that warm air from outside. If I could duct that out to the side of the building, that would be better than pulling the heat out of the basement in some cases. So ducting the intake and the discharge could be really helpful. You also now split your COP with whatever's doing space heat. So instead of kind of reducing the COP with that cascade, if we're heating the building with a gas furnace and then we're cooling the building with a heat pump water heater, this is now in parallel. So it has a better opportunity to hit those higher COPs if it's getting warm air from outside and then your space heat is from a different source completely. So condensate I talked about. Piping, are there recirc issues currently? The heat pump will not fix that. And I think that heat pumps in very early adopter scenarios are going to get a bad name completely unfairly because the DHW recirc line was so terribly performing. Unbalanced, over temperature, uninsulated, overly complex. Those things are going to affect the industry as we move forward. In a lot of cases, it may be the best money, best foot forward to start by fixing the recirc line before you do any of the water heater change out at all, because you'll set yourself up for better success there. So another thing that is kind of a game changer in the retrofit market for heat pump water heaters is this 120 volt heat pump water heater potential. So ideally, if you put in a heat pump water heater, you bring in 230 service and you've got 30 amps of power available in every panel in North America. That might not be the case, especially if the building was, even this building that I'm in, our house is a townhouse that we bought a couple of years ago, but it was built in 2018, and we had to upgrade the electrical panel. They did not give us an extra 100 amps of power to work with to add a car charger or add a heat pump water heater. So in some cases, that could be a lot of money to spend. There are a lot of rebates available, and I think more around the corner for things like that, but it could be a deterrent for some to say, I don't want to rip up the entire basement to bring in more power and upgrade our service entrance here. That seems like a lot of money just to enable a heat pump water heater. Could absolutely still pay for itself with the return on investment of the lower utility costs, depending on where you are, but it is a potential barrier. So what if we didn't have to do that? This is something that could be a very beneficial option for people moving forward. So we could have 120 volt service. We could have 120 volt service with these heat pump water heaters and store it warmer and mix down. So maybe in that case, if you only have a little bit of space like this water heater on the right here, that we can't go with a 120 gallon heat pump water heater here. It won't fit. It would be too expensive, but we could store warmer there. And that might be something that lets us kind of get through that first hour of demand and catch up a little bit more slowly, but again, could be done in a way that the homeowner doesn't even know that that's happening. So we could also do a 30 amp to 40 volt dedicated service to the heat pump water heater. I would say that's probably ideal. If you were starting with new construction for a house, I would plan for that if you were looking to do a heat pump water heater. But in a lot of different cases for retrofits, these plug-in 120 volt water heaters could be added to a dedicated circuit. Surprisingly, and check with your kind of heat pump water heater manufacturer of choice, this isn't as far behind as I would have guessed as far as recovery rates and things like that. You can use the water heater manufacturer calculators to kind of help figure this out. It's not like we're talking half or a third of the performance of a 240 volt water heater. So take a look at the plug-in 120 or dedicated circuit 120 volt water heaters, because they may not be as far off as you thought. And if we're storing a little bit warmer, we might be able to make this work for the usage profile of the home if we have a good line on what that is. In some retrofit cases, you don't even have a dedicated circuit breaker to use for the heat pump water heater. We could just plug it into the wall like it's a phone charger. Expect that you're going to have kind of a lower recovery rate if you get to that point. However, if you went a little bit bigger with storage, maybe again, nobody would even know, and you don't have to do any of that expensive electrical upgrade work. And that could be an enormous benefit. And that could really open up a lot of different projects across North America. I listened to a Tech Clean California webinar yesterday. They're kind of a program putting together rebates and incentives to get heat pump water heaters moving in California markets. They have a plumber who they interviewed who, if there is a replacement, a gas water heater is leaking, it's failing, they will come in and install a temporary gas water heater and then come back and put in the heat pump water heater once they've checked all the boxes to make sure that they're going to be setting themselves up for success and can spend the time to get everything right to do that upgrade. So you get the loaner water heater to make sure that you're not down, but you get the benefit of reevaluating the system and then not having to pay for a water heater that is an older technology if you're looking to change to the heat pump water heater. So something like that seems a little bit more complex to me. However, it could be a great way to move forward and get more heat pump water heaters into buildings if that's something that you're looking to do. It's just kind of an interesting example that I hadn't heard yesterday in that webinar. Okay, kind of related to that, there is a lot more research to be found in this Advanced Water Heater Initiative website. They've got, this is a year old. They're creating a national advanced water heater movement, a lot of research, a lot of policy level information for heat pump water heaters. That is good background information to figure out how would we do this in a way that it's going to be successful. I think just a government mandate saying no more gas ever, every everybody has to throw their gas water heater out on the lawn. We're going to come pick them up and everybody gets a heat pump water heater. Wouldn't be popular, wouldn't be effective, wouldn't help any of us, and it's going to make the plumbing industry seem like they're doing a bad job. If we can stay ahead of the curve here and see that there are a lot of incentives coming around, financial incentives, tax incentives, utility incentives, that we could use to switch to this technology, and if we know how to apply it properly and the job sites to say absolutely yes or maybe or no, that is going to help us get this technology off the ground in places that it makes sense and is a really important tool that we could add to the plumbing toolbox, as well as just as a nation, as the US and Canada, if we can get more of the BTUs off of fossil fuels, that could be an enormous motivator for a lot of people on the call. I think that that's kind of the background for a lot of this, more than people just don't like the look of gas water heaters and would like a heat pump water heater instead. That's kind of the big picture thing that we can really help enable in a pretty significant amount of BTUs across North America by doing this well, again, without interrupting the performance of the water heaters that our customers are looking for. So more information specifically about 120 volt plug-in heat pump water heaters. This new Buildings Institute study is only a couple days old as well. So this goes through a lot of different projects where they put in heat pump water heaters that were just plugged into the wall, and they'll share some of that across California, the wins and losses they had there. But that's a pretty comprehensive field study to take a look at as well. Okay, so now if we're talking about commercial heat pump water heaters, one of the questions that we had as a pre-submitted question is the COP affected by routing the building recirc line back to the heat pump? So we've got a couple examples here. We had Lochinvar came on about a year ago and did a heat pump water heater commercial focused webinar where they kind of explain how this works with some cool videos and things like that. We've got that on YouTube as well if you want to go back and refer to that. As far as how do these multiple tank arrangements work where we have flow in both directions to load them up, is the COP affected by bringing the hot water back? So if we mix out at 120 degrees and we bring it back at 118 degrees, we don't want to dump that right into the cold inlet of the heat pumps. We're going to affect our COP if we do that. We want the heat pumps to start with the cold water here, charge up these tanks. We'll take the water out of the tanks at a certain point. If we just have a little bit of temperature maintenance out in the building for the recirc loop, but it's 3 in the morning, maybe this swing tank is just kind of taking that 118 degree water and boosting it back up to 120 and sending it back out, and we're letting the heat pumps rest in that case. We want to minimize that. We don't want to drag our total building COP down by just having 200-gallon tank or a few tanks with a bunch of electrical resistance elements doing all of the work. We want to maximize the on time for these heat pumps, but we want to have really long run times. We want to have cold water to give us a high COP there. So a couple different ways to do that. We show some piping here as well for how to bring the recirc line back. Got a check valve going to the cold inlet here. If that is completely closed, which the electronic mixing valve can do, then we would have that water go back in and charge up the tanks as well. So not a piping diagram that is going to work for every single building on Earth. This is a great place to start potentially. The questions that are going to come up are how much storage, how much heat pump, and that is pretty tightly related to a question that we can't answer necessarily, is what are they using in the building? Is this a commercial laundromat, or is this a elder care facility where we don't have the same load profile for the DHW fixtures? Those are things that are going to affect how many tanks, how big the tanks are, how much heat pump, and can help you figure out what your COP could be as well. So an important criteria here, if we can close this hot port and cold port 100% with an electronic mixing valve, really simplifies the piping. It also lets us deliver 100% hot out to the building. So as I mentioned before, if we put in a thermostatic in the same example, and we have 118 degree water here and 100 degree water on the outlet here, we might be setting our heat pumps up for more work to be able to maintain that higher temperature, which we don't necessarily want, or at least we can plan around. So this is a cool project. This is from a company out on the West Coast, Small Planet Supply. This is a module replacement heat pump water heater system that they're building offsite, and then they're going to take it to a motel that they're planning to do a big DHW plant switch, and they're just going to haul this whole thing to site. I love kind of combining this best case scenario piping and insulation and installation, everything that we would like to do on site that may be logistically harder to do. They're going to do all that off site and then just drag this to the mechanical room of the motel and plug it in. It's pre-wired, it's pre-piped. I think this is the future of domestic hot water. Whether you are full on board with heat pump water heaters or not, this is going to let you cross off a lot of those boxes and get a lot of things right before you even get to the site, which I think is great. Okay, so I've got a perpetual motion machine example for you. So what we're going to do is we're all going to buy heat pump water heaters and we're going to put them right next to our refrigerator. So our refrigerator is trying to take heat from inside of the refrigerator with the warm air, warm food or whatever. It's going to spit out the hot air. We're going to take that hot air and we're going to absorb it right into our heat pump water heater, and the COP is 1 million. And I'm not taking follow-up questions on that, but that's what we could do. So that's kind of a silly example of something that we could try harder to find in these buildings, though. So one of the examples we use in hydronics is a factory that was a gelatin factory or something where they need cold water and hot water for part of the process. In that case, we can put in a water-to-water heat pump as an alternative to a heat pump water heater and take that hot energy that we're trying to get rid of and put it into the tank that's trying to absorb hot water. There are plenty of examples like that all across the commercial buildings that I've been into in my life, as far as server rooms that are too hot, wine cellars that we're trying to keep cool, some sort of industrial process, kitchens that are too hot, atriums that are too hot. Maybe if you are designing a new commercial building, put the heat pump water heater with a louvered door by the atrium or the glass hallway or something like that. Those are some of the creativity things that I think we can do, just as far as the placement in relation to other machines in a building that could help us drive up the COPs too. If we're trying desperately to get rid of solar gains on one side of the building and then pulling cold air out of a cold garage for our heat pump water heater, we're missing something there. So there's some kind of logistical changes there potentially, but I think that we could move that energy more effectively within a building. Okay, so with the last couple minutes here as kind of a review, and while I've got all of you on the call, I'd like to use a lot of free billable hours here, and I want you to help me evaluate what I should do with my own mechanical room. So in my house today, we have a 5-year-old 40-gallon gas water heater currently stored at 120 degrees. It's in the basement. There is, for the atmospheric gas water heater, there's a 6-inch duct that goes about 10 feet outside, and then also the flue that goes up through the roof. But the mechanical space is small. We're talking about 47 square feet. I don't have 700 square feet to put in a heat pump water heater downstairs without putting louvers into different parts of the space downstairs. But if I did the quickest louver to what will be the guest bedroom in this renovation we're doing downstairs, we're finishing our basement, I now have a direct louvered space from the noise, from the vibration of the mechanical room for the furnace and the heat pump water heater to a bedroom. Do I want to do that, or do I, what are my options here? So I could louver to different parts of the basement. Ideally for me would be to the hallway and not to the bedroom, which I could figure out. But those are the types of things that you should kind of look for climate-wise. So I live in Salt Lake City. I'm going to need to expect that in zone 5B, a basement is still a thumbs up, but if I'm ducting that partially outside with 6 inches of cold air coming into that mechanical room, that could be a cold space, that could be a cold mechanical room. The COP could be lower than if I pulled all of that heat from the basement, but I don't have that option because I don't have that much space without putting full louvers in all the doors or something like that. So that's okay. I just would expect that in the absolute middle of winter, I'm not going to see the COP that I would on a 100-degree day like we have today. So condensate, what am I going to do with that? I do have a floor drain, so that part is pretty easy. I don't need to pump it anywhere. That's going to be helpful. The biggest thing for me as I evaluated this as we were going through the hydronics process as well is what about power? So I had a electrical service that did not give me enough capacity to add 30 amps to do a heat pump water heater. So the basement is still unfinished, no sheetrock yet. That's the next step. I did go for an electrical service upgrade. For my house, for the space, it was $3,000 to do that. And I now have the ability to add a car charger if I got an electric car in the future, and have the space to add a heat pump water heater. It's right next to the water heater location. So I'm talking about 6 feet of wire to be able to get 240 volt, 30 amp power to the water heater. So that was something that if I had waited until this 5-year-old water heater fails in the future, hopefully that's not next year, but at some point in the next 5 years, if I'm looking to replace that, if I had finished the mechanical room and drywalled the entire basement, that power upgrade could have limited me to maybe just 120 volt plug-in heat pump water heaters. Or I think that will be the type of scenario where people say, I'm just going to do gas again. I can't spend $10,000 to rip out all the sheetrock and drag a bigger wire through and upgrade that service. It's not something I'm interested in. So for me, electrical power was the big upgrade I needed to plan for ahead of time, and a new construction is something that will be easier to do than these retrofits. So no DHW recirc, so that is good and bad, I guess. Longer wait times for hot water to take a shower, but I don't need to reevaluate the entire recirc system to see if that is something that's going to really sponge all the BTUs out of the heat pump when it's running. So local discomfort I mentioned, shares a wall with a guest bed and a bathroom. There is a spot that I could duct it if I wanted to, put some louvers in to go out to the bigger living room space downstairs. So some options there, but I would want to avoid just knocking down the wall and having the heat pump in the same room as the bedroom, obviously. That's going to lead to some local discomfort and could be a new noise, new vibration that wasn't in that space in the past, and is something that we need to plan for in retrofits especially. Again, can be overcome with different methods, but something to plan on. So I upgraded as much of the pipe insulation as I could. A mixing valve, I do have a line on one of those, so if I switch to a heat pump water heater, I can get a mixing valve and store a little bit warmer without having to go to a bigger tank necessarily. So in the last couple minutes here, should I do it? Should I go with a heat pump water heater upgrade? Should I do it right now? Should I wait until the gas water heater is on its last legs before it fails? I feel like I've prepped the situation well to do it. This is kind of the exercise here. Is it worth doing it right now? So as I go through the last couple slides, anybody who wants to give me some free design or engineering advice, go for it. And then I'll kind of wrap up here. So technical support, if you want to call and talk to us about any of the projects that you're working on, you'll get a live person. They'll look like one of these 4 guys when they answer the phone. This is a direct technical line, or you can email us. They also, Dan and Greg, do a podcast, so they'll cover some of these same topics in more of a drive to work format that you can listen to the audio of. A lot of this is ripped right from the headlines of our tech support calls, the things that we kind of have water cooler conversations about all day. And then we'd love to see your project. So if you have a heat pump water heater project that you think is a great example of how to prep and do this correctly, we'd love to be tagged on social media, and we'd be happy to like and share that content there as well. And that brings me to the end. So anybody who wants to stick around, we'll go through some of the questions that we had, and I'll have the Caleffi team see if any stick out there. And again, we'll also answer questions to follow up with an email if we don't get to you today. So what sticks out for the technical guys on the call?
Mostly no's.
Mostly no's? Oh man.
So far, okay. Yeah.
Which is fine. I mean, it depends on the situation. I want to prep for the potential to do it. I think it's kind of an interesting practical example that I'd like to have the option to do it, and I'm still a maybe. So I'm gonna have to read through the comments here. But okay, what else do you see?
I think part of your
There's
motivation too, Max, was to get the charger plug. It seems in your neck of the woods having a charger plug, for whatever reason, there's a lot of Teslas around Salt Lake and other EVs. So having that charger plug when you go to sell the place, the realtors are noticing that, and that is worth some of the upgrade too on the panel, not just for the heat pump application.
Yeah, that was part of the equation. I think that if it was $3,000 to upgrade my panel just for the potential of doing a heat pump water heater, I'd have to think about it a little bit harder. So that is, one thing to consider there. But there are a lot of places where you can get rebates for that work as well. So that could, be a lower cost to do the upgrade. Just taking a step back and not looking at it through the plumbing lens, I think a lot of things are going electric, and I'd like to have that option to do, to have more power for one electric car or two electric cars in the future, whatever that may be. If this is a house that we stay in for 10 or 15 years, it was a much lower cost to give myself the flexibility to do that. And the way that I've kind of evaluated it too, for the load profile of the domestic hot water we use in this house, a heat pump water heater absolutely would carry it. I'm not going to have to sacrifice warm showers to switch to a heat pump water heater, or even go with a 120-gallon heat pump water heater to carry the load. So I would say, kind of, tipping my cards a little bit, a heat pump water heater, I think going up one single size from a 40 to a 50-gallon, from what I can tell from the manufacturer literature, would absolutely be unnoticeable to my wife as far as a consumer of hot water in our house, and would be a good fit. And we've kind of checked enough boxes to do that. The question for me is, do I do a heat pump water heater ever? Do I do it now with a 5-year-old gas water heater? Seems kind of weird, but it could, if I run the numbers, be a good financial decision to make, or do I wait? So it depends on, will those rebates be around in 5 years? Should I just do it now? Should I not do it? Those are kind of the questions that I've had in the back of my head as we put together the webinar today, and the hydronics issue as well. So, okay, what other questions do you have? I'm seeing a lot of price questions.
Yeah, and there are a lot of application, and when you get your hands on the new hydronics, there are more formulas and more math that, I mean, you got to put in your numbers. Our numbers aren't really relevant to what your actual application is or might be, but I think there's enough COP formulas in there, room size formulas between that and the manufacturer's installation manuals, which you can get ahead of time online. You should be able to make a good decision on, if this is right for you or your customer. It's not always going to be right, and maybe in your market, most of the time, it's not going to be right, but you don't know unless you go and do the number crunching. So that's what we're trying to prepare you for here. Is we're not giving you the yes or no answer today. We're just giving you the tools for you to come up with the answer.
Yeah, and even to just kind of figure out the COP of all electric versus switching to a heat pump water heater, how much realistic COP can I expect based on these, prerequisites that I've checked? That's kind of a hard one to even say, much less to say in the state of New Mexico with an 83% efficient furnace that's preheating this air. Am I saving any money versus, what I could do instead with some of the other system examples that we've had? We have an hydronics at the end of the current issue, as well as what we've been talking about for 12 years, that a boiler and an indirect tank or something like that absolutely could still be a good fit. And maybe you use a space heating device and an indirect coil to do all this, instead of trying to get airflow into a mechanical room, if that's just not feasible. If you can get a 4-inch PVC line in and out of the mechanical room and absolutely nothing else, then maybe a boiler and an indirect tank is a good way to go. And maybe it's an electric boiler one day, but those are a couple of the things to consider. Okay. Any other?
For people that are, elevating their water heater temperature, that does shorten the life of the tank, both from, the corrosion of the tank, and also the anaerobics disappear much quicker when you start taking your tanks up to 140 and above. So if you want to get 10 years out of a new gas water heater, I would certainly recommend that you check those anode rods and replace them regularly. So it's kind of a catch-22. You want to keep, as many people noted in this chat, that you want to keep your heaters above 140 for Legionella protection, but know that's going to shorten the life and also the anode life as well as the tank life. So it's rare to get 10 years out of a tank at sitting above 140 degrees in this neck of the woods, because we've got a lot of minerals in the water. And also, you know, of course, it comes down to how much hot water you use. Every family's different. If you've got 6 kids, certainly it's going to be different than 1 kid as far as, you know, how much water goes through that tank and how long it's going to last. So a lot of unknowns here to really come up with the exact answer.
The thing you mentioned as well about Legionella, so if we're talking about a commercial building and it is an elder care facility or a hospital or something like that, and they want to do Legionella management, another thing to note here too is that with the electronic mixing valves, don't store hot all the time. Store warmer when you need to for Legionella management, but then save the life of the tank, save the ignition cycles for, you know, whatever your equipment is, by storing at a different temperature, except for the small periods that you're doing thermal disinfection. That can be a good way to kind of have your cake and eat it too, where you have the hot water advantages for things like Legionella management, but you're not always taking a penalty of storing warmer with the things that we talked about in the webinar so far.
Yeah, there were a couple of questions about Legionella Max, but in a residential application, it's not as much of a concern, right? Because you're going through pretty much every day all of your water. So you're always replenishing your system, whether you have a heat pump or a traditional boiler or a tank style, right?
Yes, and Kevin's the person to ask. He's on the working group 99 with ASPE, where they talk about Legionella. But if you're talking about a house that I live in all the time, that we're using hot water consistently, we don't have, my house isn't like some, you know, Bruce Wayne manor where I have a whole wing of the house that's unoccupied for 18 months at a time or anything like that. We use all the fixtures every day. We're bringing chlorinated water in every day. We're displacing what's in the tank. I don't have a recirc line that's, you know, sitting stagnant anywhere or anything like that. So those are some of the things that, without having to do anything, we're kind of reducing the opportunity for those Legionella colony forming units to grow. In a residential example, where in a big unoccupied skyscraper during COVID, we haven't checked any of those boxes, and we need to look at that a lot harder, but that's kind of a topic for another day, I guess. All right, any other questions we should grab in the webinar, or should we go ahead and close it down?
I think we hit quite a few of them as we were going through here, but there's going to be a few that we'll have to get back to you on that are going to take a little bit more time and research to help you out on that. But we will, between Max and I and some of the other team, we'll get back to everybody that either pre-submitted question that we didn't cover or the ones that came in during the process here. But thanks for a record-breaking event, everybody, both on signups and attendance. So that's in what, 12 or 14 years that we've been doing this, this is the best one ever. So thanks everybody for helping us with that.
Yeah, the interest is high, and that was part of the reason we picked this topic for hydronics and Coffee with Caleffi. I guess my follow-up advice too is that if you've got specific questions about the equipment or about your location, check with your manufacturer's rep who sells whatever your favorite water heater is and say, okay, what do you have for heat pump water heater applications? I live in Alberta and I currently use this. What would I have to do, or what would I expect? They're going to know more regionally. Then we can kind of make generalizations there. And if you're in those, you know, 1 through 3 climate zones, it's going to be a pretty easy technology to adapt. If you're in the cold of the Rocky Mountains, then there may be some other things to consider, but there's still opportunity to evaluate this and find a good home for heat pump water heaters if it fits the criteria that you're looking for your customers. So I guess I'll end it on that. Thank you again for attending today. We appreciate the support with these webinars. We'll see you in a month for John Siegenthaler's air to water heat pump evaluation of a specific project profile. So thank you again, and we'll see you soon.